So I thought, so it's good to see so many of you sitting and trying to work out problems. And it's a good thing because we are all at different various ages, various levels of knowledge, various levels of enthusiasm, and for the subject, etc. So it's good that we are each sort of gets whatever he or she can from the what's going on, and then handle it accordingly. Okay, but all the same, I thought that maybe 2 weeks of quite a lot has happened, and maybe some review of some basic results and some basic things and some clarification may sort of help you a little bit and remove some of the hopelessness that might have just a little bit set in. I mean, if it has not set in, I'd be no problem at all. But in case it might have set in, I just want to not leave it to chance and try and make an attempt to alleviate it. Okay? So, so like I said, I just wearing the mic now, but I'll be happy to give it to any of you. So let us just see what all we have learned. So Humphreys is the book that we said we are following, right? Not very literally, I suppose, but we are. That's the book. As one of my colleagues said, the advantage of having a book is that you are free to do whatever you want. So that's the way we are using it, in the sense that you read Humphreys, we do what we want. So, I mean, it frees up the lecturer to attend to things that are maybe better left to the, to avoid things that are better left to the text, and to concentrate on things that are perhaps better done, conveyed through a lecture. Okay, that's the idea. Okay. So, and also there is this infinite dimensional stuff that is thrown in, which one lecture I gave and Punita gave 4 already. So we've had 5 lectures on that. So we can review some of that and understand, or better still, put into black boxes what we don't understand and try to manage our lack of understanding. Okay, that's a better way of putting it. Okay, because it's very difficult. It's as you know, it's a subject with a more than 100-year-old history. The classification theorem, which Vishwanath talked about, of root systems and hence of semisimple Lie algebras, dates from the year 1898, Cartan and Killing. Okay, so it's more than 112 years old. So, and it's one of the great subjects of mathematics. So it has been worked upon and embellished since then. One of the embellishments being this Kac-Moody algebras. Okay, so it is impossible to sort of learn it all at one shot. So it is reasonable to try and put into black boxes what we don't understand, accept this as a fact, and go on and try to use it rather than worry about how it is proved, or not being too much worried about why it is true, or etc. Okay, that's the idea. Okay, so let us see what all. Maybe one of you should come up and list a couple of theorems that you've learned. What are the theorems or important definitions that you've learned? Okay, we know the definition of a Lie algebra, and we know the definition of what a representation is. Those are the basic objects that we are talking about. That's the basic language. But a little more than that. What are some of the things that in the last 2 weeks you've understood maybe that you didn't understand before? To put a finger on something, some particular thing, nice thing that you like, that you didn't know before and you have learned now. Any one of you please would volunteer? Venkatesh, let's ask Venkatesh. Maybe he knows all about this finite dimensional thing. So anything in the infinite dimensional thing that you liked, or? Okay, so I hope to get some of you to the board, but I'll wait. I'll wait for that. Okay, so here is, so let me start with this. So there is this, what are we studying? This is what the blurb on the net says. So we are studying complex semi-simple Lie algebras. And here there are two aspects, interrelated, but roughly you can say, for at least for logical purposes, you can separate them. There is the structure theory, and there is the representation theory. Okay. So what is the simplest example of I remember that was my first year in Chennai. I had just joined CMI as faculty when Sheshadri was giving lectures on complex semi-simple algebras and Kac-Moody algebras. So after a first definition, somebody asked him, what's an example? So he said, wait, at the end we'll do all the examples. So, meaning he meant the classification. So he didn't want to get his hands dirty with any particular example. So in fact, we have done all the examples, right? Not just one, but all. But we will. So here is how I would like to, when I'm lost, I try to just think of what it is for SL2. Okay, and I think that if you're lost, that's something that it's a course correcting mechanism that you can use. Okay, so here is the simplest example of an algebra, the unique simplest example in some sense, because there are no algebras in dimensions 1 and 2. There is only one simple algebra in dimension 3, semi-simple algebras, which is also simple, and that is this. Okay, this is the simplest example. And any question, like for example, whatever Sendamarekannan did this morning, he was writing those P's and Q's, etc., and epsilon lambdas, etc., and then proving several relations among them. Okay, now if it may seem like all mysterious, and so the thing to do if you're lost is, what is it for SL2? How do you write it? Can I prove it? And very often you can write it down. It's very nice and very explicit, and you can prove it. And very often and then if you tell me the general statement, I'm willing to accept it, okay, without worrying about a proof. That's one kind of technique which you can use. I mean, of course, each of us is built very differently, and surely Sheshadri didn't follow this principle. There are different ways for different people. That's appreciated. But this is one possible way of understanding something if you're lost. Okay. For example, what is the Weil character formula for this? Or well, you have not seen the Weil formula yet, but you will see it in Sendamare's next lecture. And you could try it and write it down for this. And in fact, it's an exercise in Humphreys which says work it out explicitly, prove it for this. Okay? So that is one thing you should do. And where both the structure theory, so of course we have these famous elements X, right? These elements, and there is representation theory which we talked about. This is there is complete reducibility. And there is, if you remember in my second lecture, I talked about this. So one property of representations, of finite dimensional representations, is that, So this representation theory we will talk about is always finite dimensional, although we are talking about, for the sake of the finite dimensional representation theory, we are talking about things which are not finite dimensional. But our final interest is only in finite dimensional representations. But for example, Sandhamara was writing Z lambda, and we had to talk about this maximal vector, maximal vectors and universal objects with maximal vectors. These are infinite dimensional objects. We are talking about them for the sake of finite. Finally, in the end, we are interested only in the finite dimensional representation theory. Okay. By the way, if you are interested in the infinite dimensional representation theory of this, it is something that one could be possibly interested in, and there are, I understand, not that I know very much about it, that there are many open questions. Okay, it's an interesting thing, but for now, let's just worry about the finite dimensional representation. So there is complete reducibility. There is also, so what are the other theorems? So we are reduced to understanding what are the irreducible objects, and what is the parameterization of the irreducible objects? It is by non-negative integers. So irreducible, irreps, let me write, irreducible representations are in one-to-one correspondence with the set of non-negative integers. So here if you call it lambda, here we call it V lambda. More generally, this lambda could be some dominant integral weight. That is the word that is used. Okay. Now, if you don't like the word dominant integral weight, just think a non-negative integer and think of what it means for SL2. Okay. That's one way of simplifying the thing to try and understand. Okay. So, and we said dimension of V lambda is lambda plus 1, and in fact we wrote down what, so this a model for V lambda was this, the way we wrote it was U lambda, the span of right. So, and now let me start with the character of V lambda. Let us review that. Okay. So first of all, where does this live? So what do we understand by that? Okay, one use of these characters, I repeat, this bears repetition. I said it in my lecture on SL2C, but it bears. So you can manipulate, this is very often forgotten. You can manipulate with characters just as you do for finite groups, complex representations. Okay. So to find out things about representations, you can just reduce to the characters and do it. Just like the characters determine the representations there, they determine the representations here. Okay. So to understand how, for example, two irreducible representations, the tensor product of two irreducible representations will decompose, you can take the character of this, multiply that just as purely formally polynomials or functions, and then try and manipulate that and get an answer, and lo and behold, that gives you the answer. And that works in general, not just for SL2, it works in general, although it's a little more complicated. And if you keep this, that underlying idea is used repeatedly. For example, in yesterday's proof of Chavalet's theorem, and the center of the universal enveloping algebra is the same as SHW. So yesterday Sandhamara proved this, or CH in his notation. Okay. There again, in this same kind of, again, try and do this for SL. Understand what this means for SL2. What do you get on this side? That's an interesting thing to do. Okay. So, okay. So now let's talk about this. What do we mean by character? First for SL2, but also in general. So what is the character? So So from group theory, we understand that it is a trace of all objects, right? That's what a character is of an irreducible representation over a finite group. Okay. Here we do slightly something different. Now, to see, like I was trying to tell you, to see the analogy with groups, you have to actually think of them as rather group representations rather than Lie algebra representations, and do then the analogy between this and the finite group case will be much more clear and transparent. Okay? But since we are committing the sin, as Upendra must have told you in the first day, we should have actually studied Lie groups rather than Lie algebras, but that the reason why we are not doing that is because Lie groups involves many more so to speak prerequisites, and we can't handle, if you want to gather 30 people from diverse backgrounds, this is one meeting ground where you can, rather than worry about knowing about differentiable manifolds or and other stuff which many of you may not have been exposed to. Okay? And in any case, finally you will have to do this anyway. You can use this as a means for learning that. That's the idea. And there is the infinite dimensional theory and the theory of Chauvet groups that is going to come next week. Those are things that are very important. In fact, the paper by Chauvet introducing Chauvet groups, that was in the 1950s, the group theorist. Okay, so it's a very important. It's surely one of the most important papers ever written in mathematics. Okay, so it's not by doing Lie algebras, it's not that as if we are not doing anything important. We are doing good stuff. There is no question about that. I don't need to be apologetic about it. Okay, so let's do what is character of V lambda. What is it? So you have this element H here, right? More generally, you would have this Cartan subalgebra, right? These elements act semi-simply in the adjoint representation. And one of this is the preservation of Jordan decomposition says, you take an element of the Lie algebra, semi-simple Lie algebra. If it acts nilpotently in the adjoint representation, then it acts nilpotently on every representation. If an element acts semi-simply in the adjoint representation, then it acts semi-simply on any representation. Okay, this is an important fact. So that tells me that H acts semi-simply on this. You can split H into eigenvectors. You can split this V lambda into eigenspaces for the action of H. More generally, this will be here. If you look here, each element acts semi-simply and they commute with each other. And so you can split the representation into common eigenspaces that are common eigenspaces for the action of every element here. All right? Okay. So here is I'm using V sub lambda there. Already there is some conflict of notation. V sub lambda was also used for the weight space lambda, yes. Right? So V bracket, okay, thanks. So I will change this to V round bracket lambda. Is that Humphreys' notation? Okay, so let us, and also let me change lambda to mu, just for, okay, so mu is an element of H star. Okay, if mu is an element of H star, this is defined as, and V is any representation. Then you can, this is V in V such that H of V is equal to mu H of V for all H in H. That's an important definition. These are the common eigenspaces. Okay? And so you can write V, this, by the way, the preservation of Jordan decomposition says for any finite dimensional G module. That's the statement. So if V is a finite dimensional representation, then I can write it for this H if it's SL2, more generally for the Cartan subalgebra, as that's the weight space decomposition. That's called the weight space decomposition. Okay? Now, of course, this V itself is finite dimensional. Therefore, each of these V mu's is finite dimensional. And this looks like an infinite sum. You are summing over this parameterizing set is over a vector space, all elements of a complex vector space. Okay? There's lots of elements there, but actually only finitely many of them happen to be there. Okay? And okay, so okay. Now what you do is, so mu in H star is a weight of V. See, the word weight is used in many different senses. Okay? Weight could be just an element of H star. A weight of a module could be the space, is a weight of, this is a definition, if V mu is not equal to 0. That's another definition. Okay? So the word weight is used in many different ways. Just get used to the context in which the speaker is using that word. Okay? Okay. So what is, so let's come back to this. So I take a finite dimensional representation, say for SL2. I know that it can be written as like this. In the case of SL2, mu is in H star. H is what for us? H is the line spanned by this capital H. So what will be H star? H star is another one-dimensional complex line, meaning it's a complex line. It's a one-dimensional complex vector space. Each element there I can parameterize by a complex number. If I take mu to be that number, I can say I call that linear functional mu if its action on this given H is mu. That's how I, okay. So I can identify H star with C. That's the identification I make. Okay. Now, what is the theorem that you have learned about what values mu can have? So if I take some finite dimensional SL2 module, break it up like this, now mu could be, the way I have written it, mu could be any complex number. What? They have to be integers. Okay? So these mu's have to be integers. Okay? So mu in the case of SL2 is an integer. What is the corresponding statement for a general complex semisimple Lie algebra? The mu is in the yes, mu is the integral weight. Okay, now I am going to ask you what is the definition of integral weight. Okay, so more generally it can be mu is an integral weight. That's correct. So there are two questions that stare at us are, what is an integral weight and why is it so? Why should weights be integral? Why can't I have a weight that is 1/2? What is the problem? Okay? And there is a very simple answer to this, which you might have lost in that argument appeared several times on the board, but I will point it out so that you can if you have, I mean, I'm not, it's easy to miss it because there's so much has happened. So so first of all, what is an integral weight? Pardon me? integral values. Here you will say on H. No, but surely it's a linear functional, correct. It should take integral values on. So this H is okay. But in this case, surely no functional can take integral values on the entire vector space. So you have to single out some special elements and say, like this H, and say that they take integral values on those. What are those special elements? Okay, let me remind you for that. Okay, so they are called the co-roots. Okay, co-roots. So that is, so this is the definition is this of this. So mu is an integral weight. That is, mu takes integral values on the co-roots. So now we've transferred the burden of definition to what co-roots are. Now we have to understand what co-roots are. So I guess we have to understand what roots are before we come to co-roots. So what are roots? Yes. There are simple co-roots, there are non-simple co-roots.
So
but
these are all integral or integrals?
I could have replaced that by simple co-roots, and that would have been enough. You're right. Is that what you're referring to? There are co-roots. There is a co-root associated to every root. And so if there are simple co-roots and non-simple, and it's enough to demand that they are integral on the simple ones, because the non-simple ones are sums of integral combinations of the simple ones. So that would be enough. But for the moment, we can be more, we can say it like this. Okay. So what we want to understand, therefore, what the co-roots are. But so that gets us to the question: what are the roots? So how do I define roots? Okay. So the thing is, you take the God-given representation, namely the adjoint representation, look at its decomposition into weight spaces for a given Cartan subalgebra. Okay, see this, you have made a choice here. Okay, and the theorem that has not been stated yet, which Upendra will do it next week, is that it does not matter. There are theorems in the book which say that no matter the choices you might have, I might make a different choice than yours, but in the end we'll have the same answers. Okay, so you, with respect to this Cartan subalgebra, you have, so roots are, you take G and write it, when you decompose G as eigenspaces for H, then this theorem about root space decomposition says the following. Of course, H is commutative, so all elements of H will act as 0 on H. So there will be a G sub 0 which will include H, but actually which is equal to H. Okay. So there is a G sub 0 which is equal to H, and there is a G sub alpha, some finite alpha. So these, so let me introduce this notation. So that's the set of roots. So alpha in H star is a root if G sub alpha is not equal to 0. So, and what is the definition of G sub alpha? It is just this with alpha in place of mu. So let's write it down. G sub alpha is nothing but all x in G such that H acting on X by the adjoint action is alpha of H times X for all H in H. And it's a root if this, right? Okay. Now what is the?
So this definition is specifically for the adjoint.
Yeah. So in another way of saying it, roots are the weights of the adjoint representation. That's the. You can make the definition of weights in general. You're saying roots are the weights of the adjoint representation. Okay. And now the beautiful theorem is if you look at the roots, I mean, of course, we are going away from co-roots, we'll come back to that, but if you look at the roots, they form a root system. In fact, they form a reduced root system. That is, if you, let me remind you what the definition of, so in the definition of root system we made, there were 3 conditions. Okay? So see, that is a completely, combinatorial object. It's a completely combinatorial definition. You have a Euclidean vector space, or maybe Vishwanath did it even with a, Humphreys does it with a Euclidean vector space. But Vishwanath's definition was more general, the Bourbaki definition, where he didn't even have a Euclidean vector space, but any vector space. Be that as it may, what roots are, a root system is some vector space on which either you are given a Euclidean structure to begin with, or there is a Euclidean structure at the end. So you might as well assume that it's Euclidean, that is that there is an inner product. And there are finitely many vectors with some, there is an arrangement of finitely many vectors with some very nice properties, right? Namely, that if I take the reflection of that these, okay, let's remind ourselves of the axioms for a root system. These finitely many vectors span the vector space, that was one condition. And what was another condition? So you take the reflection, since I am assuming it's a Euclidean space, given a vector, I have a orthogonal hyperplane to it. The reflection in this hyperplane preserves the root system. Okay? And and then you could write down a formula. So S alpha of V, you could write as V minus 2 times V alpha by alpha V. So this would be, it's easy to write. This is a very nice exercise to do if you haven't done it. I mean, this is how the reflection will act on a general V in that V, and that the third most important condition, or not most important condition, but important condition was that this should be integral. That's the integrality property. So the roots form a root system. Okay, that's a theorem. It's not easy to prove. It's what Upendra did in maybe 1.5 to 2 lectures. But the point is that the roots form a root system. It's a very beautiful theorem, because we've started off with some Lie algebras and made some definition and got somewhere, and then finally we are saying this, we are getting something that has a combinatorial structure. Maybe that's not so surprising. Even more surprising is the theorem that this root system determines that Lie algebra fully. Okay? So there is a one-to-one correspondence between simple Lie algebras, of which so you build semi-simple Lie algebras by taking direct sums of simple Lie algebras, and simple Lie algebras correspond to what kind of root systems? Irreducible reduced root systems. Okay? So roots form a root system. Okay, now but let's come to the roots now, co-roots now. So what is a co-root? So if let alpha be a root, let G be semi-simple and alpha a root with respect to, of course, some h. To be precise, I have to say it that way. I've made a choice of a Cartan subalgebra and there is a root. Okay? Now I know what this means, right? This is what we have defined. So, or let's make one more. Let's make one more general statement, very general statement. I have this notation, right? G alpha. I have this notation. And if V is a representation, G acts on it, so this makes sense. This is some subspace of V. Will this? Yes, this is an easy calculation. That's a very basic one. Okay. So if I take G alpha and G minus alpha, now I'm thinking of this as, if you want to, I think of this adjoint representation in minus alpha, then of course I have to do this. So where does this live? This lives in G sub 0, which is H. Right? But this is, but these are one dimensional. Right? These are one dimensional. So what can be the image? It's either one dimensional or 0 dimensional. Can it be 0 dimensional? Okay, it can't be 0 dimensional because then there will be a problem with the thing that the killing form is non-degenerate, and there will be problems with that. Okay, let's not worry about what the proof is. For the moment, let's accept that it is actually one dimensional. So what you see here as the image of this, so the image in H is one dimensional. Okay. So let us work out an example of what this might be. Okay. So for example, in SLN, okay, so the standard way to take that would be H, right? The traceless matrices. Okay. Now what are the weight spaces? What are the weights of the adjoint representation, which will tell me what the roots are? So I look at what is the basis for SLNC? The traceless diagonal matrices, and if I take them away, then the EIJs is a natural basis, and it turns out that these natural bases are also give me the root space decomposition. Okay. So this is the root. So if I take EIJ here, that's a root. So if I take a root, for example, here, let me take E1n. So E1n, that lives in this. So G, so I could write SLN, so let me try to write it. SLNC, that's my G. Alpha would be this root, the root corresponding to that. What do I mean by that? That actually is a linear functional on the Cartan subalgebra. That I write as epsilon 1 minus epsilon n. What does it mean? It acts on a diagonal matrix and maps it to the first entry minus the last entry. That's what it means, right? Is equal to C E 1n. That's what G alpha would be in this case. Okay. So if I take C E1n, and the negative of that would be the one here, that would give me epsilon n minus epsilon 1. That's a small calculation which we are by now familiar. So let's perform this and tell me what it gives. E1n with En1 is what? Is E11 minus En. So this is C E11 minus En. So that is low and below. So this is the span of this line. The line spanned by 1 minus 1, the rest zeros. That is this space. That is the one-dimensional image. Okay? The image is always one-dimensional. Okay. And further notice, here is another fact. Again, let's not worry about the proof. Again, all the proofs are driven by very simple facts. It's one simple fact after another. No step is difficult, but they come at very quickly and in wonderful combinations. here is another fact. You take this is a linear function on the Cartan subalgebra. Here I have a one-dimensional sub. I can restrict this to this one-dimensional sub. Alpha restricted to is, in this case, what is it? If I take this alpha, this is something here minus something here, and I restrict, alpha is what? Alpha is epsilon 1 minus epsilon a. So what do I get? So an element here would be lambda minus lambda, or C minus C, where C is a complex number. And if I apply epsilon 1 minus epsilon n to it, what do I get? I get 2C. Okay? So it's non-zero. So the statement is never zero. So that linear functional restricted to the line does not vanish. Okay? That's a fact. So there is a unique element there on which alpha takes value 2. Namely, this 1 minus 1 itself. Because if you take 1 minus of minus 1, that's 2. That's the unique one that gives me 2. Okay? So there exists unique element in G alpha, G minus alpha, such that alpha of that element, that is the co-root. This element is the co-root. It lives in the Cartan subalgebra. It is denoted variously. Some people write H alpha. I always get confused. Humphreys writes T alpha sometimes, and then H alpha. He has a T alpha and a separate H alpha. I don't know which notation to follow. I call it alpha check, which is what the notation used in the infinite dimensional correspond. So there are, okay, the point is there are many notations used in various books. So if you are confused, you look back in the book that you are using, make sure that the author is, you understand what the author means. Okay? So there are many different notations used. So this element is the co-root alpha corresponding to alpha. Yes? Yeah. So I am saying this linear functional alpha, the root, that's a linear functional. When you restrict it to this one line, which is G alpha, the product of G alpha and G minus alpha, which is a line in this Cartan subalgebra, it is non-zero. So you have a linear function on a line, and if it is non-zero, then there is a unique point on which it takes value 2. And that point of the Cartan subalgebra it lies by definition in this G alpha, G minus alpha, that is called the corresponding co-root. That point in the Cartan subalgebra is the co-root, denoted alpha check, sometimes denoted H alpha, sometimes denoted H alpha tilde, H alpha prime. Okay? There are many different notations. I am very confused, so I don't know which, but so different books use different notations. That is the co-root. Okay? So the co-roots are a set of elements in the Cartan subalgebra. What are they in the case of SLN? It's very easy to see. Suppose I give you the root Eij. Tell me the corresponding co-root. 1 in the ith position, minus 1 in the jth position. That's as simple as that. So the beautiful thing in this theory is, although it's very complicated, you can keep a concrete example in front of you, and if you try to do it in that concrete example, so all the thing goes away. And very often the concrete example contains enough structure for you to, believe things, if not actually be able to prove things about the general setting. Okay? So we understand what the co-roots are, right? Now read that. It takes integral values on the co-roots. Okay? And why is this so? Why is this so? The reason why. Okay. So we have done what co-roots are, and therefore we know what integral weights are. Namely, they are elements of the root lattice. Sorry.
All this was to do with adjoint representation.
This statement itself is about a general representation.
Yes, I know, but this particular.
See, we got there because we wanted to define co-root. All this is to define co-root. So if you want, I was there and all this was an aside on roots and co-roots because we wanted to define what co-roots were. Okay? So the theorem is that in a finite dimensional representation, the weights are integral. That's a statement. That's the statement. What does it mean? It means that mu takes integral values on the co-roots. In the SL2 case, it means that the weights that you get are integers. What it means is, see, technically, on the face of it, there is no reason why in an SL2C module, if I write a module and break it up, H should not act as 3/4 or by E or pi or some strange number, right? But it does not do so. H acts always as an integer. Okay, the corresponding statement is that all these co-roots act by integral values. That's what it means. The eigenvalues for these co-roots are integers. Okay, they don't act by some strange things. They act by the eigenvalues for the co-roots are integral. It's a very strong restriction. And what is the proof? The proof lies in SL2C theory. See, the proof, let me remind you of the proof. I will not do it in great detail, but let me remind you of the proof. The proof is like this. Suppose there was a non-integral weight. Okay? Suppose there was a. So here is something that I did in my lecture. You can go back and check. Okay? So before that, let me come to another point, which is again a very general thing and of great applicability. Now, so what is a maximal vector? What's the definition of a maximal vector? Anybody wants to? Sorry? Go ahead, please. Killed by the positive, the root spaces which are positive, right? So it's first of all, it's an eigenvector for the action of, it's a weight vector. Again, I'm using the word weight in a different sense. What I mean is it belongs to one of these weight spaces. Secondly, it is killed by all the G alphas alpha positive. So for example, in the SL2 case, it means X kills it. It is 0 for the action of X. And if it is SL2, it means SL3, it means it's killed for E12, E13 and E23. It's killed by the actions of those. Okay? Why should that be? And it is a weight vector for H. Okay? The claim is such a thing always exists. And the reason is very simple. It is this. Okay, so for example, let's do it in SL2. So there are finitely many, the other root spaces are 0. So look at the one, I'm writing this as a real line, but imagine in the complex plane, also, there may be several points which indicate my weights. There are finitely many points which are weights, and I am at some place here, one of the extremal things on this side. Okay, if I hit it with an X, take a weight vector and hit it with an x. Where should it go? It should go to the weight space which is plus 2 to that. It should go into this weight space. But there is nothing there, meaning it is 0. So it is 0. It is that simple argument just souped up, which tells you that there is always a maximal vector in a finite dimensional vector space. That is the origin for, yeah. So maximal vector is a weight vector killed by x alpha alpha positive root. By x alpha, I mean an element below, right? I mean, it has various meanings, but at the moment, let me change that to this. Okay? Killed by the root space. Such a thing always exists because of this argument. You can carry out this in a more general setup. The thing will not be a line, but will be some bigger vector space. But again, you go to some extremal point, and then it can't be pushed, so it always exists. Okay? Maximal vectors exist. Okay. Now, what is the next argument? That's why all this theory that Anupam talked about, maximal vectors, how you take maximal vectors and that's why they are important. Okay, because of this reason that they exist, and using them you can try to understand the structure of the representation. Okay. Okay. So suppose now let's think of V as a maximal vector. I know it exists. Okay. Now, okay, let's look back. So I want to understand the structure of representations. I know that every representation is a sum of irreducible representations. So I'm down to irreducible representations, let's say. Okay. Then I know there is a maximal vector. Okay. And I can take this, the action of the universal enveloping algebra on G. This is a sub vector space containing V. So it's a non-zero submodule, G submodule. Therefore, if it is irreducible, it is all of it. Okay. So this is the reason. So I can try to understand. So every irreducible module is generated by maximal vector, very trivially, because maximal vectors exist, and because it's irreducible, it has to be generated by the maximal vector. This submodule must be equal to V. So we'll try to analyze. By anything, it would be generated in particular by the maximal vector. Correct. Okay, so let us try to understand this. In the case of SL2, let's try to do this again, and again that works more generally. Okay, it's just the argument is souped up. So if I try to I have to produce. Now I try to understand the module itself by acting various elements of UG on this. What do I do if I act H? I get back some multiple of it. That's no good. Meaning I already know what to do with it. If I act X, it moves up, but that's 0. In fact, there is no place to move up. It is a maximal vector, which means XV is 0. So what can I do? I can act Y on it. So you act Y on it. I can act Y square on it. And if you act back X on this, it goes back here. If you act back X on this, it goes back here, etc. And so you have this line. But there is a very subtle point here. So I have this. Okay, so now let me write this in this notation, which I am very fond of. Rather than n, I will just divide by n factorial and write it. You will see a lot of this next week when we talk about Chevalley groups. But for the moment, you can just take it as something that is an idiosyncrasy. So if I hit this with X, it goes up, is what we said. Does it always do that? In the sense, if I hit this with X, it surely has to go up, but can it be 0? If you understand this, you understood this. This what I'm going to write down in a minute, which I wrote down in the SL2C case in the lecture itself, the argument for this is nothing more, nothing less than this basic observation. So the question is, how does, if you recall, we wrote an equation like this. What was this equal to? If this weight was lambda, this is lambda minus 2, this is lambda minus 4, and so on. Lambda minus n plus 1 y to the n minus 1b. That is what it is. It is a very important equation. Okay? It is innocuous, but it holds the key. It is the key. Okay? Now, observe, it is finite dimensional. Therefore, some of this is 0. So, look at the first place, something is 0 and the next one is not. This is non-zero, this is 0. How can that be? And this is, that is why it is integral. This shows lambda must be equal to n minus 1. The same argument souped up, which I am sure if you look back now at Anupam's notes, will have the same argument. This nothing more, nothing less than this. You can actually just use the same argument literally by just restricting to the various SL2 pieces in your. See, what does it mean to say that it takes integral values? It is integral on every coroot. Now, I want to prove that it is integral on a particular coroot. I take the corresponding SL2 piece sitting inside that SLN or that G. What is that? That is G alpha, G minus alpha, and the line generated by this coroot. I take that. That is an SL2. You restrict that module to this SL2 and argue, you will get this. So, I have given you not just idea of the proof. Okay. So, this is the reason why it is integral, because otherwise you have to keep going. If you, so that's the reason. If I had stayed half, if I started with half, there is no way that is going to get killed by any power of y. I must get minus half, minus 3 halves, minus 5 halves. I must keep going. Meaning, if I subtract 2, I mean, maybe I said it wrongly. Half, I mean, then whatever the next, minus 3 halves, minus whatever it is. Okay? So, what I have to keep going. I can't stop because this equation will be violated. Okay? So, that is why one of the important things is it should be integral. Weight should be integral. That is an important theorem. Okay? So, where are we? What should we say next? We started talking about the character. So, let us try and get there. Let's see, I am afraid this would happen. I am doing all the talking. I mean, maybe it is time that we stopped and somebody else, maybe Shiva, why don't you? No, I mean, if one of you could come and ask some question or say something, would that be? Okay, let us try it for another 10 minutes or so. Let us break for tea, and then when we come back, let us really try to do it. I will try not to wear the mic so much. Okay, so let's get to what the character is. What is it? Okay. I repeat, the character, you can manipulate it. The reason why we are interested in it is that it holds the key to the representation theory. Just like in the finite group case, characters determine the representations, and you can play around with characters to get out the information about the underlying representations. Okay? That is the reason why we are interested in characters. But what is a character? Okay? Now, so we have these weight spaces. They are integral. They take integral values on the. Okay, now let us make some definitions. So, these weights were initially elements of H star, right? They were only elements of H star in here. Okay? But among these, there was a notation introduced, lambda. I think Sandamara used lambda. This is the integral, so the weight lattice. Again, you see, we are using the word weight in so many different ways. I think it is called a weight lattice, or more correctly, the lattice of integral weights. What is this? In the case of SL2, can you tell me what this lattice of integral weights is, this is the set of integral weights. That is the weights, that is the elements of H star which take integral values on all the co-roots. In this case, there is only one co-root, namely H itself on 1 minus 1, the element 1. So, what is that set? What is? Yes, but so if I on H, it should take value 1, right? So, it is represented, if my H star is represented by a complex line with the identification that any complex number, by a complex number I mean the corresponding functional which takes that value on H, then the integral weights are in particular the integers. So, with that, but more correctly it is epsilon 1 minus epsilon 2 by 2, because that is the one which takes value. Epsilon 1 takes value 1 minus epsilon 2 takes value 1. So, 2 divided by 2, that is the one which takes value 1. That is that, as an element of H star, it is this. And the root itself is here. This is the root. Epsilon 1 minus epsilon 2.
That's why the half when you did one.
That was where so the half sum of the positive roots is 1 for SL2. Okay. So, this is 0, this is minus 1, and this is minus alpha, root alpha minus alpha. So, epsilon 2 minus epsilon 1. Okay. So, the weights have to be integral. So, for example, for the standard representation, the weights are 1 and minus 1. Why? H is eigenvector, acts as with eigenvalue 1 on 1 0 as minus 1 on 0 1. Okay. Okay. And there is a lot more structure on what the weights can be, how they can be distributed, what if one weight space has some multiplicity, I will talk about multiplicity in a minute, what the other multiplicity can be, etc. And there are many formulae describing these relations, and that is what Sanamara is going to do. He talked about Constant formula, Weil formula, Steinberg formula, Freudenthal formula, ever so many formulae. Okay? So, whatever they are about the distribution of these weight spaces and their multiplicities. Okay? But let us try to understand it in some particular case. So, this is H star and this is the weight lattice or the lattice of integral weights. This is contained in the root lattice. Thank you. Why? Tell me why the root, what is the root lattice? It is the integral combinations of the roots. That is the definition. So, for example, in the case of SL2, what is the root lattice? Even integers. Integral linear combinations of the roots. Even integers are the root lattice. The weight lattice is all integers. This is something good to keep in mind. Okay? And the root lattice modulo the weight lattice is Z mod 2Z. That is another important thing. That is an important number attached to the group or the Lie algebra. Okay? But never mind, we will probably not see this in this course. So, tell me why the root lattice is contained in the weight lattice. Very good. It is the integrality property. The integrality property is just saying that the co-roots are integral on the roots. That is that property. Okay? This is the integrality property. Because it is a root system, and you have this integrality. This is because, I mean, when I say because, you can think of it, see the roots form a root system, and then you see the third property of integrality, that is just saying that the roots are taking integral values on the co-roots. So, in particular, they are weights, they are integral weights, okay, because of integrality property. of the root system. Okay. Now let us come to, so I look at a particular representation. I know now that they are integral weights. Okay. I look at this weight space decomposition. Now I understand that they cannot be arbitrary elements of H star, but are elements of the integral weight lattice. In other words, they are, in the case of SL2, they must be integers. Now I look at something and I decompose and look at the weights, the weight spaces. There may be 5 here, 10 here, something, right? So I could draw a picture of my V as 0, 1, 2. So if these are the integers, I could look at the dimensions of these spaces, V0, V1, etc. And at integer I could write dimension of V sub I. So let me draw a picture. So I'll draw a small circle, big circle, depending on, this is just a very schematic picture of big circle if the dimension is big, small circle if the dimension is small. Okay. Now the character is something that just keeps track of this information. And the point is, this information itself determines the representation. It's a remarkable fact. If you know this information, first of all, the picture that I've drawn is randomly. There is lots of structure on what those sizes of those balls can be. Okay, if you turn Fulton Harris's book and you look at, so he has these kind of pictures, 1 circle, 2 circle, 3 circles, etc. And there is a lot of structure on what, if something is 1, something else has to be 1, something cannot be 2, etc. Okay, there is lots of structure, and if you have this information, the character is nothing more, nothing less than this information coded in a particular way. And if you have this information, that representation is determined up to isomorphism. Okay, remarkable fact, right? I decompose it, look at the dimensions, and then that's it. I know the representation fully up to isomorphism. Okay, no two representations have the same character. They are isomorphic. If they have the same character, they are isomorphic. Okay, that's the fact. But how do you encode this information? This is just that formal thing about Z lambda. That is just some formal mechanism to keep track of this. Okay, and it's formal, but it's also easy to manipulate. It's like good notation. Okay, so what is that notation? So see, this weight lattice now is an abelian group with respect to addition. Just like here it is integers. In the case of SL2, it may be a more. So in the case of SL2, SL2 is okay. SL3, it's something that lives in R2, if you wish. Okay, in a two-dimensional space. By the way, I'm talking of R2. See, already I made a jump. From a complex line, I came to a real line. Why can I do that? Because I have said that on the roots they are integral, and here is another important thing. See, the roots are some space living in H star, right? And there are many of them. For example, in SL3, how many roots are there? 6 roots. 6 roots living in a what dimensional complex vector space? 2-dimensional. 2-dimensional complex vector space, 6 roots. Okay. Now you take the real span of these 6 roots. That could span the entire complex vector 2 vector space, right? Because after all, it has only 4 real dimensions, and I am taking 6 roots. Okay, that's possible. Okay, you might say one is the negative of the other, so remove them. Still, I have 3. Okay, so, but the fact is, this is another fact, that if you take the real span of the roots, that's what is called a real form for the complex vector space. That is, it has the same dimension same real dimension as the underlying complex vector space. So I'll say that. So here is another fact. So R, the real span of the roots is a real form for H star. What does that mean? What does the word real form mean? What it means is you denote this, what should we call this, W or something? No, what's a good letter for? So it's actually called H sub R star or something like this. But so I'll write R alpha sigma alpha root. Okay, that's the real span of the roots, right? This that's what it means. See, if this has too much dimension, this will not inject. If it has too small, it will not surject. It has the correct dimension. The real dimension of this equals the complex dimension of this. So the roots, although there are 6 of them, in the case of SL3, they span exactly a 2-dimensional space. Okay, that's a fact. Okay. I mean, that is embedded in the statement that the roots form roots. I mean, the roots form a root system.
But all these root systems were drawn in R2.
No, the pictures, there are many which are not in R2, right? Like, for example, for SLN, they will live in they live in H star, whatever that dimension is. Okay, for SLN it would be n minus 1, SL10 it would be 9-dimensional. Yeah, so the examples drawn were examples of all the 2-dimensional root systems. Okay. So that's why I was drawing the real line, sort of. I'm even justified in drawing the real line because the root, and therefore the weight lattice is in particular, the weight lattice also lives in this. Okay, so the weight lattice is also lives in this space. So the weight lattice actually lives in here, in this space, without the tensor with C. Okay. Now let me just introduce this notation and stop there and come back. So how do we keep track of this information of these weight spaces, the dimensions of the weight spaces? And I said that the character does it, and what is the notation that is used? Okay. So you have this lambda, which is an abelian group. So lambda is an abelian group, right? I can add, so it's the integral linear combinations of weights. Weights are certain points in a vector space, so I'm taking integral linear combinations from them. So I can add, so it's an abelian group sitting inside H star, that big complex vector space, but also in the real span of the roots, for example. So when we draw pictures, we are actually drawing, when I draw this line for SL2, I am drawing the real span of the roots sitting inside H star. That's what we are doing. So lambda is an abelian group. So what do I want to know? What is the character? So on this abelian group, on certain points, I want to keep track of certain extra numbers. How do I do it very nicely? Here is one device that is used. Abelian groups are of course written additively. This one in particular comes in a vector space. So it is written naturally additively. But I write this multiplicatively so that I can form the group ring. See, if I form the group ring, the integral group ring, That's a nice the integral group ring will, what is an integral group ring? It has finitely many, it has support on finitely many elements, and with each element I associate an integer. Okay, I only want a natural number, not even an integer, but okay, let me say integer to begin with. So I slightly enlarge my class of objects, things I am looking at. At every one of these integers, I attach another integer. That's what I want to do in some nice way. So for that purpose, I treat this abelian group, I write this write lambda additively. Oh, sorry, multiplicatively. So the device to do that is, instead of lambda, you write exp of lambda or e of lambda or any of one of those devices. Okay. Now I can talk about z. So this is what Sennamarai was writing, z lambda. This is nothing but the integral group ring of this group, but group rings, when you write group rings, you want them, the common convention is that the group of which you are taking the group ring is written multiplicatively. So you write this multiplicatively and take the group ring. So what are the elements? Elements are integral linear combinations of group elements. So they are of the form n lambda, e lambda, lambda is in lambda. N lambda are integers. Integers, n lambda equal to 0 for almost all lambda, right? This is where the characters live. This is the ring in which the characters live. So I can now add characters, multiply characters, and divide, maybe I can try and divide one thing by another, possibly. If you have some liking for formal mathematics, if you want to write formal power series and manipulate things, then maybe that's a subject you should consider seriously as working in. Okay, so now I will just break for tea with just one example. Let us write the character of a few simple representations of SL2 in this notation. What would they be? This I did earlier also. So what is V0? This is the trivial representation. What is its character? E to the 0. That's what it would be. V1 is the standard representation. What is its character? There is x, h and y. X corresponds to eigenvalue. H eigenvalue of x is 2, h eigenvalue of h is 0, h eigenvalue of y is minus 2. So I write E2 plus E0 plus E minus 2. And more generally, V sub n or V sub lambda will be e power lambda plus e power lambda minus 2 plus dot 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 plus e power 2 minus lambda plus e minus lambda. N lambdas are the so I forgot. So character of V is equal to, this is definition, sigma lambda is in h star or lambda is in lambda if you wish. Dimension of, let me write mu because that lambda, okay. Let me write mu. There I have written, I have erased it, but I wrote mu there. That's the definition, okay. Now let me just write the Weil character formula in this special case and stop. Okay, the Weil character formula just says e to the lambda plus 1 minus e to the lambda minus 1 by e1 minus e minus 1. It is just that simple expansion. And Humphrey says, prove this, which we have proved. All you have to do is do this and see it's equal to this. Okay, so this is the special, this is the wild character formula. More generally, it is written sigma, W is in W, e to the lambda plus rho, or sorry, sine of W times e to the W of lambda plus rho divided by W is in W, sine of W, e to the W rho. You work this out for this and see it's W is two elements. Okay. So, well, anyway, so maybe we should break for tea for a few minutes and come back if you still have energy, and I hope somebody else will do some talking other than me.